birds are waking me up. I never knew how good they're able to sing. Soft, cool bed and pillow talk, while the sunbeam slowly moves and hit the sheets. 3-4 hours of sleep, and my shades can't save me now. The sun is just a preheat for the night that's about to come. But I just lost my phone, and I don't know where to go. No, my friends are getting stoned, somewhere on a boat. Yeah, though I feel alright by a drifter's side, strangers on the go. That's all I have to know. Worries fade into light. I hold it warm and we dance through the night. Our favorite song is stereo, while the sunbeam slowly turns into stars. 3-4 hours of sleep, and my shades can't save me now. The sun is just a preheat for the night that's about to come. But I just lost my phone, and I don't know where to go. No, my friends are getting stoned, somewhere on a boat. Yeah, though I feel alright by a drifter's side, strangers on the go. That's all I have to know.
Hey robot makers, hope you're having a good day so far. So do you want to learn all about how to use servo easing in your robotics project? Then this is the show for you. So I'm just turning my volume down there because I can just hear it pinging up. I just wanted to make sure it didn't distract everyone. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let's get over to our keynote and make a start, shall we? Okay, yes. So this show is all about how to do servo easing, and if you've used any servos in the past, you might be wondering like how to do this or even what this is, and it's probably a bit simpler than you would think, though it does require a bit of stitching together. So we're going to have a look at what servo easing is, why you need it, how it works, some simple maths depending on how your maths is, and how servos work. We'll have a quick recap on that. I had a nice little animation that I did about a year ago, and I've just borrowed that because it works so well. And then we'll have a look at some of the different easing algorithms, and then we'll get into some flipping pancakes. So one of the reasons that I was building this servo easing thing was because I wanted to work on Bubo Tutti, my steampunk robot, and I wanted its eyes to sort of open and close in a very sort of smooth, natural kind of motion. And rather than trying to burn out the any further servos on that, I thought what I would do is basically just have some servos attached to something that could rotate round, and I could see like a little flag. And that got me thinking about what could I do to make that a little bit more interesting, just as a little showpiece. So I built another little robot that's called Pancake Bot, because Tuesday this week is Pancake Tuesday, so we're going to be using it for that. So we're going to demo that and show you how it can flip. There's a little frying pan and some little it's just here, just sat on my desk. I can show you there he is. He's very, very small, and his pancakes are even smaller there. So, and there's Bubo just sat on the desk next to him. Okay, let's get back to our notes there. So what is servo easing and why should we use it? So servo easing is a technique to improve the smoothness of movement with your servo motors. It's achieved by using a mathematical algorithm to adjust the acceleration and deceleration of the servo as it moves between two positions, its start and its end position, over a period of time, its duration. And this helps create a really smooth, natural motion that can reduce motor noise and wear and tear. And it also makes it look, a lot more natural, a lot more I don't know, anthropomorphic perhaps. So how does servo easing actually work then? So this little graph, we'll see this quite a lot in this show today. This is kind of a time versus position graph. So it doesn't matter how long the time is, that's just a period of time. And it actually doesn't matter what the start and end position is. The algorithm will just adjust the amount between both of those positions, the start and the end. And we're aiming for this just on our little humble servo. You can see we've got the official Kev's Robot servos there. It's amazing what you can do with a bit of rendering. So what is easing? This is probably the easiest way for me to show you easing is. The diagram on the left, you can see that it doesn't have any easing, and it's just moving in a sort of a linear fashion at the same speed between 2 points. And one of the things that this can cause problems is when it abruptly stops, you get a bit of like backlash, you'll get a bit of extra energy from the motor going back through the circuitry, and that's not desirable. And it can also like jar, depending on how much weight is on the servo, it can be quite jarring of the mechanism. And you can see on the right hand side there, with easing, it's a lot more smoother, a lot more fluid, and it's sort of slow to start, fast in the middle, and then slows at the end. And that's an ease in out function, and we'll have a look at that in a second too. So let's have a quick recap on how servos work. So a servo, as you may or may not know, is a little motor that we can use to move a little horn on the top. So the servo horn, that little white plastic bit, that's the bit that we attach parts of our robot to. Might be a leg or limb, an eyelid, anything we want. The shaft of the motor is sort of presented to the servo horn, and that will turn given our instructions. We've got the little connector there. We've got somebody just joining there. Thank you, String and Sealing Wax. I'm just going to turn off Stream Elements for a second. We've got 2 people subscribing. Thank you both for that. So yes, we've got the little connector on the end there. I'm just trying to see if I've got a spare servo. I have indeed. Let me just grab that one. You have these little connectors on the end. They always have these similar kind of wires. It might be a yellow, red and black, or it might be orange, red and brown, depending on what particular servo that you've actually got. But I love these little DS 929 MGs. They're a very small but very powerful little metal gear motor. So that's what they look like on the outside. You've also got these two mounting points either side, so you can put some screws in and firmly attach that to something. And then we can magically now take away on this diagram here the outside layer, so we can actually see what it looks like inside. So this is like the inside of the servo. You don't normally get to see this. So the internal components, we've got a little gearbox. Now that gearbox on the cheaper servos, looking around to see if I have a cheaper servo, probably not to hand. I don't tend to use them as much nowadays. They tend to be that transparent blue colour. That's how you can usually tell. And the bit that you connect to, the little bit on the top there, that bit will also be plastic, and inside the gears will be plastic. And that's okay for cost. It brings the cost right down, but it does mean as the gears are sort of moving, they will over time sort of move around and wear down a lot quicker than a metal gear will. So a metal gear is what we really want to aim for there. Underneath that gearbox, you've got a DC motor, a tiny little motor, and it's just like a regular DC motor. It doesn't have any intelligence. It can either spin one direction or spin the other, and that's it. And that's connected to a little control circuit, and the control circuit is the thing that connects to this little cable and receives all those pulse widths that we're going to send it, and we'll look at how that works in a minute. And that then also has a connection to a potentiometer. So if we've looked at potentiometers before, looking around if I have one of those to hand, I don't think I do actually. And basically that's just like a variable resistor. As you turn the knob, the resistance value will change. And that's actually pushed onto the end of the shaft. So as that's turning around, we can actually detect what position that's in, and therefore have we achieved the angle that we're shooting for. So Adam says the stream is dropping. Let me just check out, see if there's any issues there. What I'm going to do is just drop off here for a second and see if that improves it. Bear with me. See if that stays live. Okay, I've just turned off my Wi-Fi connection. Sometimes it tries to switch over to that and then we get some issues, but I think it should be okay. Let me know how you're finding that. I can see it's a bit low, the stream at the moment. Are you getting any problems there, Alex? It's about 2 megabits. It should be 6. Yeah, if you refresh your browser, that can sometimes help it, but I am seeing a bit of lag there. Hopefully that won't interrupt too much what we're doing. So that little control circuit will take the pulse widths and it will convert it into an angle that it's aiming for, and it'll turn that motor until it achieves that angle as read by that potentiometer. That's the little feedback loop that we get there. Okay, so that's how they work inside. Let's have a look. So I actually disassembled an actual servo just to have a look and see, does it actually look like that? It's exactly like that. You can see the little control board there. You can see where the wire goes into the bottom there. There's a little chip. There's the 2 wires that go to the DC motor, and that's got a little gear on one end. There's our gearbox, and underneath here, which you can't quite see, is the potentiometer. So that's just underneath that shaft there, and that's all the sort of casing for the servo. And that's a little DS929MG that sadly died because I burnt it out with Bubo. Okay. So we talked about pulse width modulation. This is how we control servos. And what this means is, if you imagine there's a period of time, which is 20 milliseconds, and what we're going to do within that 20 milliseconds is pulse. We're going to send like 5 volts high across our little signal wire, and we're going to do that for 1 millisecond. And 1 millisecond will tell the controller that's plugged into this on the other end, that's other end of this cable inside there, tell that controller to turn the servo until it's at 0 degrees, whatever 0 degrees means on that particular servo. And if we double that, we would get 90 degrees. If we double that, we get 180 degrees, so it would swing around the entire other direction. And then halfway between that, so 1.5 milliseconds, that would be 90 degrees in this particular scenario. Now, those values can change. It can be more or less than that. But this is quite a common way of doing the pulses. So 20 milliseconds, 50 megahertz. And that duty cycle is the 20 milliseconds. It's how long we between pulses. And we basically just make the signal go high or low between that to do it. Now, we can do that in the background. Now, there's an awful lot of libraries in Arduino and MicroPython that will do all this kind of stuff for you. In fact, the Pimoroni Servo 2040 library, which I'm using the Pimroni Servo 2040 on a lot of my projects. They've written a servo class that hides all that complexity for you, so that you don't have to know how many pulse widths to do to achieve what you need to do in your projects. But that's how it works in the background, so just be aware that pulse widths are something that translate into angles. So transition and easing algorithms, there's quite a few of these, and essentially there's 3 different types. We're going to cover what those are. So we've looked at linear, which is like no easing at all, so we go between the start and the end position over a period of time, and the value doesn't sort of start and stop, it just goes it increases at the same rate, is what I should say. So there's no easing at all applied there. And easing in is where we start off slowly with not very much value, and then we get more and more value as time goes on in that sort of... this is using the circular one. We'll have a look at all the different types in a second, but you can see there it's sort of easing it in to the very end point. So on that one, you're going to rapidly increase till you get to the very end point where it'll then stop. So that's easing in. Next is easing out. That's where we start with a sort of quite strong value, and then we slowly over time that the value becomes less and less. So that would make the sort of servo start quickly but then slow down to a stop. So that's easing out. And then there's a mixture of both of them, which is called ease in out. You'll see this a lot on animations on web pages, for example. They have ease in out. It's a very common function that's called easy ease in Adobe After Effects, if you've ever done any animations, and it can help do things like bouncing and so on. It just gives that sort of very natural start slow, speed up and slow down. And that's what was happening at the beginning on that animation of the leg that we saw. So the amount of the values, slow acceleration, in the middle it has a more fast acceleration, and then towards the end it will slow back down again. Okay, so some of the common algorithms that we will see, we have the linear tween, there's circular, cubic, exponential, quadratic, quartic, and quintic, and then finally sinusoidal. So these usually shortened to a different term. So again, we've looked at linear. If we did linear ease in, ease out, or ease in out, it would look exactly the same. There's no easing applied at all for that. Now, as I go through these next couple of slides, if you just generally keep your eye on, and say, the middle one, you'll see the shape get more extreme depending on which of the algorithms we choose. So I've ordered these specifically to show that increase in the amount that's being applied. So if we start out with the sinusoidal, it's quite a general, it's a little bit more than linear, but you've not got very much easing going on there, but it's quite a nice amount. You can see there that's quite a smooth, gentle curve. We now move to the next one. You can see that's a lot more extreme, so circular, a lot more extreme. We move to the next one. This is quadratic. This one is even more extreme. Then we've got cubic, and we have quartic, quintic, and then we have exponential. And look at that, it's almost going straight up, so very slow, and then all of a sudden it'll go very, very fast. Now, depending on what your use case is for this, you might want to play around with these to get different behaviors on your robot, but certainly you want to pick which one suits best. And you can only really do that through experimentation. So if you like what I do and you want to help grow the channel more, help me become more successful and produce more robot videos ultimately, please make sure you give this video a like, drop me a comment, let me know how you're finding the stream and previous shows, and also make sure you subscribe to the channel as well. It really helps get other people on their homepage. They'll see this appear, the more people that subscribe, and you'll get notified too. I do go live every single Sunday at 7 o'clock GMT. We're in regular time now, so we're on GMT +0. The reason I say ish is in British summertime we're like +1, but we're now aligned again with Greenwich Mean Time. Okay, so here's all the different types of easing. So it's easy when you know how. There's a lot of different, there's actually more than these 8. There's a lot more. There's bouncing ones, and what's the other ones, elastic ones. There's all kinds of quite funky ones that change value. So like the bouncing will make it like a bouncing ball. so rather than being a curve, it will actually change it depending on what the duration is. You can see that we've got the ease in, the ease out, and the ease in out for each of these as well. And again, you can see that the curve, if you like say look at the middle one, for example, you can see we start out flat, then there's a bit of a curve, and then that curve gets more and more extreme as we get to the exponential ones at the end. And we'll have a look at how these work behind the scenes in a second. So how do we add this to our code then? So we've got a servo, we want to do some easing. How do we actually do this? Well, we're going to do this in a loop. So rather than just sort of having the servo, you know, say move to a particular angle, what we're going to do is we're going to have a target value that we want the servo to move to. We're going to have a start value that we're going to start from, and we're going to have a duration of time of how long we want it to do that transition, that animation of easing. So we need those start, target, and duration values. And then we also need to pass it a current time value as well. And really that's all we're going to pass the easing function, is just the time. And it will basically, because it knows what the start value, the target value is, and the duration, it will be able to work out very simply what position it needs to be. So that's all we need to do, is just say the angle, the ease will give us back the value that we want to set our servo to, and it's as simple as that. Looks complicated, it isn't when you get into it. So that's what we're going to be doing behind the scenes. And I thought I would show you a different technique this week using Jupyter Notebooks, because it really brings this code to life. So let's get over to that. I'm just going to put it on for me for a second, and let's see. So how are we doing on the stream? Is everybody getting a good signal there? I'm not sure if it's buffering a lot. Normally I get like about 5 megabits. I'm getting about 2 and a bit at the moment, so I'm not sure what's going on there. I don't know if that's causing anybody any issues. Hopefully it's fine, and you can see the stream okay. So I'll wait for a couple of seconds. Yep, working okay at the moment. Great stuff. And in HD. Perfect. Good stuff. Right. Okay, let me get over to Jupyter Notebook then. So let me just bring that up, and let me share my screen. Okay, so I've got Visual Studio Code, and I've got the Jupyter Notebook plugin installed as well. So you can install that just by going to the plugins, the marketplace extensions. But it's very, very simple to use, and you'll be able to download this code that I'm going to include in the Bubo 2T repository as well. So the way that these Jupyter Notebooks work, you've got blocks of cells, and each cell can either contain text or code. And because of that, we can break our program into little like retestable units, which is really nice. So I don't need to run that very first block there, that import sysexecutable pip install matplotlib. There was a weird bug that I was finding that I needed to just have that included once for it to work, but it's fine now. So if I now execute this next cell, there's a little play button here, and what this is going to do, this is going to import a library that I've created that's called Easing. We'll have a look at Easing in a minute, but basically that has in it the linear, the easing quad, easing out, all the different algorithms, it has those in there. We're also going to import NumPy, which is a like a data science thing. It's just a nice easy way to play with numbers in Python. We're going to import that as NP. And we're also going to import matplotlib, which is a really nice plotting, like charting tool, and we can draw some graphs, which is quite cool. We can do that in here, which is really, really neat. Makes it very, very simple to do. So if I just run that, it's run that number 6 in that little brackets there just tells me that the code is run. So does that little tick, and that didn't take any time at all to do that. Now this next block of code is a bit repetitive, and essentially what I'm doing is I'm creating a variable, and the variable is going to be of a particular type of algorithm that we've just imported, so linear, easing, quad, and so on. And we're going to pass it the start value, the end value, and the duration. So these are just arbitrary numbers. These could be angles, these could be whatever we want to use here. So they're all going to have those 3 in that sort of same formation. And then the other thing I'm going to do is some of them I've actually named nicely, and some of them I just left as like letters of the alphabet because I was lazy. But essentially I should go down and just rename all of these to be like ease out quad, ease in out quad, and so on. But I'm not going to use all of these today. I've just got them in there. But you can see that there's a great big block of code, and it does the same thing, but just for each of the different algorithms. So I've got a whole bunch of variables, one for each of the different types of easing thing. The next thing I've got is this X, And this X is going to use this NumPy function, which is called aRange, and aRange is going to return, in effect, like a list of values, and we're going to basically create some data for our chart to show you the different types of graphs. So you don't need to worry about that too much, but I'm just going to run that block of code there to create all those variables. So they've got number 7, it's ticked the thing. And we're now going to generate the data for our charts. And again, this is a bit repetitive, and we're going to pass in, we're going to create a list, and the list is going to map the linear values that we've just created and those X values that we've just created there. And it's going to store the results in a variable that's called x1 or easing quad x. Again, don't worry about this. This is just to generate our chart data. So I'm going to run that, and that's finished running there. We've got the 8. Now, let's plot the linear easing. If I click run, look what happens. This is now within our Jupyter Notebook. It's outputted a little chart. So what I can do is I can add that chart just by clicking on here to like a list of plots. So that first one is sort of stuck in there. I can save that out to disk as an image if I wanted to. We can look at that further. And you can see there it's starting at the value 3. And it's dropping all the way down to the value 1, which is what I asked it to, and it's doing that over the duration of 1 second. So you can see how that works. And you can see there, that means our linear easing algorithm is working as we expect, because we've got that sort of 45-degree line that we expected. Okay, next up is, let's see. I'm just watching that comment that just came in there. YouTube just dropped to 144p, and I had to manually reset to 720p. That's weird. I'm keeping an eye on the bandwidth again. It looks like we're struggling a little bit there, and I'm not sure what would be causing that. That's a bit frustrating. There's nothing I can do about that. Let's keep an eye on that, and let me know if it gets any worse, and might have to like reboot a router or something like that. But it should be okay for now. Great, Richard said it's working fine as well. Okay, so next up, so that was our linear. Let's try the ease in quad. So we're going to run this one, and we're going to get 3 different ones, because what I've done here is I've actually plotted 3 different, the ease in quad, the ease out quad, and the ease in out quad. And we can see on our little plot there that we have all 3 represented. So that's the ease out, that's the ease in, and the green one is the ease in out. So you can see it's quite a nice gentle curve there. Let's run the next one, which is the, well, I'll tell you what, I'll also just go and hover. If I hover over that one there, I also get like this little pop-up thing that just momentarily appears. And if I click that, it means I can add it to our plots. And we can sort of build up a notebook of plots. We can do the same with this one. So if I click on that button there, we can then see that's got a much more extreme version. So quad, cubic. Let's go back to our notebook. And you get the idea here. So we can do ease in quart. That one looks even more extreme. Let's add that one to our little charts list there. And let's see what we have next. So, oops, let's just run that one there. This is the quint. It's getting further and further apart, you can see, and looking more and more extreme. Let's wait till we get to the exponential one. That gets even crazier. You can see there, sort of thin, thicker, thicker, really, really thick. And let's go back here. Let's run the next one, which is the sinusoidal. This one's quite an in-between one. We'll add that one to our plots. You can see that's probably just before the quad one, I would think, in the order of things. Next is the exponential. So look at this. This is really extreme. Let's add that one in. Yep. And then let's go back, and then let's run the last couple. So we have circular. Let's add that one to our little plot thing, and we can see what that looks like. So again, that's looking somewhere between cubic and quart, I would think. I don't know if you can drag these, can you? No, you can't. And then what else we've got? So there's a couple of others that are included in the library, but I've not really tested them. So ease in elastic, not sure if this one actually works. Yes, it does. It does work. So elastic looks like it's going to snap. So rather than easing, it kind of just does the kind of motion like that. So you can get your servo to sort of like flap around as if it was like on a piece of elastic. So yeah, And what the other thing that we can do as well, just using matplotlib, is we can put them all onto a single plot like this, so we can compare them side by side. We can even give them colours and names and so on. We just give them colours by just adding the tab orange, tab brown and so on to the plot. So check out Jupyter Notebook, check out Matplotlib. It's really useful for checking your code. This helped me test the easing algorithms and visualize them to see that they were working fine in a kind of abstract way, because I didn't even have to look at the actual servo itself. I could just look at the plots and see that they were working the way that I would expect them to. So that's Jupyter Notebooks, a little tool I use quite often when I want to experiment things, because what you can go back and rerun that particular cell at any point in your program. That's one of the things I like about it, as well as those charts that are in there too. Okay, it looks like the bandwidth has really crept back up again now, which is good. So we shouldn't have any further problems with that, I'm hoping. Okay, so we looked at how to do the different algorithms. How do we then apply that to our actual servo? So what we need to do is we need to set our servo each time we go through a loop, and we need to do that over a period of time, which is our duration. So if the elapsed time is greater than the duration, i.e. we've missed our chance to move the servo properly, we can basically just have this little cheat here which just says set the current angle to be the target angle, set the servo value to be whatever the target value is, and then we need a short sleep when we're setting servos to give it actually time to move. If we don't do that, the servo won't move at all. And then if that's not the case, so if the duration is less than our elapsed time, if the elapsed time is less than duration, I should say, then we can basically just say the angle becomes equal to the ease. And the ease is going to be passed in the elapsed time, and it will then give us back the value that we need to set the angle to. So that does the actual work. This is just like a routine to make sure that even if the servo algorithm fails or something, it will actually move at the very end of the duration to the angle that we need it to. So it's kind of a capture thing. And then the elapsed time is simply the start time minus the current time, and we capture that at the very beginning in a variable that's called start time. And we can use the ticks ms, which is the ticks in milliseconds. There's a ticks ns as well, I think, which is like microseconds, which is like 1,000 times more than milliseconds, to grab the current time. And because we're using MicroPython, we might not necessarily know what time actual like clock time things are. We can just get the number of seconds that are pulsed since the unit was given power. So there's somebody ticks since it's booted up. Okay, so if you want to learn more, there is some stuff I've been building out this courses repository. They're all free as well. So if you go to kesrobots.com/learn/, you'll find all the different courses. I added one this afternoon, which was how to build a Smars robot. I actually just borrowed that from the other site that I run, which is the Smars fan site, but I thought I might as well put it all in one place. This is a bit of a nicer experience, I find. Okay, so I promised pancake flipping, so let's give this a go. So what I've got on my desk over here, if I go over here, you can see we've got this little robot. He's got a little pancake, which is like a tiny little, almost like a coin-shaped thing, and it's got like it's just got some filler on the one side, just where it came off the 3D print bed ever so slightly weirdly, but that'll help us see which side up the pancake is. So I'm going to put it in that side of the robot there. Let's go to another camera view so you can just see what he looks like here. So he's kind of like a cube shape, and he's got like a little spatula in one hand, he's got a frying pan in the other hand, and he's essentially just got two servos there. He's got a little hat as well. That is probably the most delicate thing I've ever printed. It's like 1 millimeter thick at one point, so how that hasn't snapped off yet, I don't know. And I'm also running this just using the Servo 2040 from Pimoroni. So that's just, oops, let me go to that one there. That was just slightly off camera. If I can zoom back, you can probably just about see there the Servo 2040, which is just over here. Not sure why that's out of focus, but there you go. Okay, so let's just zoom back in so we can see a bit easier what's going on, and I'll just make him sort of centered just there, and then it's just the wires are just coming out and going straight into the servo. So that's what he looks like there. If I go over to here, I'll be able to get the code up and we can give this a go. So I've created this little program. I'll show you full screen first. That's just called Chef, And this was just me playing around with some MicroPython. I'm basically trying out all the different easing algorithms to see how that works. And let's just have a look at, so I'm bringing in the SuperServo. So what I've done is I've created a new class that's called SuperServo, and that will basically just make it really easy for me to take the Pimoroni servo library and slap a few extra bits and pieces on there, which is to do with the easing. So I'm hiding all that in there. I'm calibrating the arm, which is the frying pan arm, so pan arm, and I'm basically just setting the values between 0 and 180. I did this because I wasn't sure whether I wanted the arm to go all the way back and then all the way forward, but it actually worked out fine, so I could probably actually get rid of that calibration. But you can calibrate using the Pimoroni servo library between any values, and this can protect your servos from burning out. And in fact, this one that burnt out that I have on my desk here, this one burnt out, it was in one of Bubo's eyes, and the eyelids would go that far back that the motor would start straining, and it was straining on my desk quietly and getting hotter and hotter, and then I heard it sort of making this sort of crackly sound, and that's the signs that it's just about to die, and it wouldn't really work very well. So rather than that happen and the motors be strained, I need to work out what's the maximum value to send it back to and the maximum value to send it forward to, and then calibrate those just using the calibration function. I've then created a start position and end position. I've got those in capitals because it's a constant, because I'm not changing that through during the running of the program. And the duration in seconds, I'm making this 1/4 of a second, so we can play with this and make it really slow to see what's going to go on, but we'll leave it at 1/4 of a second for now. And then we set the start angle to be the start position, so 120, and the target position is the end position, which is 50. So these are degrees in our motor. I'm using the ease in quint, because that one seems to be the one that I wanted to go for. It gives us the more sort of flick for our pancake. And then what I then do is there's a function I've created that's called tick start, and that will reset the time, the current time. It will reset the timer within our servo to say this was the start time, this was the tick start time. And then when it's looking at the current time, it can see how many seconds or milliseconds have elapsed since then. So that's what that does. And I think it also just sets the other variables within the super servo as well. This show function will just show us what the current values are. It's just helpful for debugging. And I then also do the duration in seconds, the start angle, the target angle, and the elapsed time in seconds as well. I've created these in seconds ones because it works internally in milliseconds, and sometimes that's not helpful. So having it just times that by 1,000 just gives us, or divide it by 1,000 gives us the actual seconds. Then we're going to print out what the current tick value is, whether it's true or false, because it will return every time we tick the servo, it will return a value true or false to say whether it's finished doing the animation. Now this means we can set an animation within our robot, and we can basically have a loop that ticks forever, and it doesn't matter because it'll do the animation and then the animation will have stopped, but we can carry on doing the ticks and it'll ignore them. Now if we have something that feeds it like an external value, so say we have a Bluetooth controller, or it's receiving some instructions from somewhere else, we can have all kinds of different pieces of code that will change the animation that's going on, and therefore the ticking thing will just animate whatever the current positions are. So while not arm.tick, then tick, and then show the results, and then just show the elapsed time. So let's run this and let's see what happens. I'm just going to split the screen like this so we can see at the same time what's going on. And I'll just move this up a little bit just so we can see. So I'm going to hit the run button. It happens pretty quickly. So there we go. He's just flipped his little pancake. And what I might do, because he doesn't flip it every single time, I'm going to put like an X on one side just to make it a bit more easier to see. So there's like a flat side. So what I'll do is I'll just put like a little X on one side. So he doesn't flip every single time. Let's see if we can get him to flip this over.
Centre the pan.
What's that, Alex?
You want to centre the pan?
I can centre the pan. Do you like that?
Yeah.
Right, and let's get that a bit over to that side, because like a real, and I'll just move it down ever so slightly. There we go. Let's see if we can get him to flip this over. Has he done that? No, that's still the X on that side. It's just a bit of light I'm going to keep doing this until we get it flipped. It does do it, I promise you. There we go, he's done it. He's flipped it over. So the X is on the underside. So if I move this over like some kind of magician, I'm just going to show you there, the X is on that side there. There we go. So he flipped his pancake, and he's done that, and we're using the Quint algorithm to do that. And we'll have a look at some of the code as well, so you can see what's going on here. So if I go over to, I'm in Thonny. I don't write my code in Thonny, but I find it's easier to run code because you've got that little shell down here, and you've got the little file system, and everything sort of just works nicely there. So we start out with this transition base, and this is just like every one of our easing algorithms is going to have this within it. So it's going to have a start, end, and duration, and we're going to bring those in at the very beginning. It's going to have a function for easing, and we're not going to implement that in this base class. We're going to implement that elsewhere. And then we've basically just got this little piece of code here which does some things you don't need to worry about, but essentially it just figures out what angle it needs to be. And then for each of the different easing functions, we then define what they need to be. So linear simply takes in the time and returns the time because it doesn't change any aspect of the angle. The ease in quad basically times the time by itself, so you get a quadratic multiplication of that. The ease out quad basically does the reverse of that, so minus t times t minus 2. The ease in out has to check whether it's halfway through the animation or not, so there's this if statement, and it basically just either does the ease in or ease out one depending on what the time is. The cubic does it by 3, so we get like that 8 or 6 time times time times time, so that's like a cubic multiplication there. And if we go down to the quart one, we get times time times time times time, and then obviously the quint one is 5 lots of that. There we go, time times time time time. So you get this this increasing one. And the exponential one, if we scroll down to that, let's just find the exponential one. That one uses the power function that's within the maths module to figure out, is it an exponential increase? And if we just go back to the ease in sine, so we're using the cosine or the sine functions to work out what they are. We need pi divided by 2 to figure out those. We get those very nice, gentle, rounded curves with those ones. And if I scroll down, there's some other ones as well. So we've got the circular ones. We have the elastic ones, which do that weird sort of bouncing effect. And there's another one, I think, in here, which I've not tested, which is the ease in back. So these ones look very interesting. I've not run these ones, but we could probably play with those too. So they're inside the easing, and in a sense these are really abstract. They don't do anything other than just some math. They just return a value given a time input. The SuperServer one is my way of wrapping all that together. So I'm bringing in my easing functions, bringing in the Pimoroni Servo class from the Servo 2040 library. I have this very short sleep thing to just help my servos move into position. I've got the mapping angle thing there, which is one of my favourite little functions, which can take in a value and map it between 2 different inputs and then provide an output between 2 different outputs. So this is great for converting, say, pulse widths into angles or vice versa. And then our SuperServo class has a transition value. We can basically just pass in a piece of text like easy in sine, and it will then figure out which algorithm we want to use. So it just makes it a bit easier, and it hides all the complexities like the start time, the change in angle, change in values, the maximum minimum values for the angles, the duration, the current angle, the target angle, and the tick start time. So it takes all those things and sort of hides them away. And it will also have this ease variable, which will encompass our easing function. So we then basically just assign it from a pin. So what pin is this connected to on our GPIO? And then I'm giving it a name, so like leg or arm or frying pan, something like that, which is helpful for debugging. And we've got this minimum and maximum angle as well. We've got the calibration function, and basically that just passes it straight through to the 2040's calibration code. This is quite a useful thing that you can add to your code if you want to do something useful. You can create a class that has a Dunder, which is a double underscore string double underscore. And that means if somebody prints out the name of the class, it will basically return a string of whatever we put in there. So this one will, if we do this down here, if I just say import super servo, I need to do bubo.superservo because it's actually in a folder that's called bubo. You can see on the right hand side there. I basically just created a little library to have all these things in there. So if I do that, if I do s equals SuperServo, is that going to work? I need to give it a GPIO number, and that's probably enough. And then if I do s.name, for example, let's call this Kev's live stream servo. And then if I just print out s, it will run that string thing. So you can see that it's returning the name, the minimum angle, the maximum angle, and the current angle and the target angle. So there we go. So that's a really nice thing you can add to your classes to make them super useful. And then we've got some other things. I've got quite a few things in this class. So there's these properties, and these are sort of getters and setters of values. And they can be a bit redundant, these, if you're not going to use any of the special functionality within them. But I like to include them in there just for robustness. So for example, on this angle setter, rather than just setting the internal servo angle, the current value, I'm also setting the servo's angle itself. So when you set the angle, it will actually move it to that and then do a short sleep. So we've got a couple of other properties in there. The transition setter, this is the way that we can actually pass in a string of text to say, you know, set the transition value to be like ease out circ. And if it's within that, if the value that we pass in is a valid transition, then it will set the transition type to be that value. And if it's not, it will basically just say that's not a valid transition type. So if we go back down to here, we do like s dot transition equals, and let's just pass it some nonsense. Nonsense is not a valid transition type, whereas if we do like linear, linear isn't, do I have to do it linear with a capital L? I can't remember how or linear tween, that's what it's called. Looking up above the screen there, linear underscore tween, and that's a valid type. So behind the scenes, it will basically say if the value is linear tween, then it will say the else function that we have becomes equal to the new transition, which is linear tween, and the start value is whatever we have as our start angle, the target angle, the end value is our target angle, and the duration is whatever we set the duration to. So if we do s dot duration equals, I don't know, 3, that's now going to be 3 milliseconds, I think. I can do set duration in seconds instead, like that. If I just print out s dot duration, so let me just go back there. So remember, I've got two different things. I've got duration and duration in seconds. If I print out duration, 3 seconds is 3000 milliseconds, whereas if I set the so if I did like 10, the duration would be then 1,000 times that, so 10,000, and so on. So this is like a nice little helper thing, and if we scroll up, we can see how that works behind the scenes, and it simply just multiplies the duration by 1,000. I think it's further down actually. Let's just find that. Yes, this is not great code here, but it works. So yeah, duration in seconds essentially just returns what the current duration is divided by 1,000, and when we set the duration, it just sets that internal double underscore duration value to hide the complexities and inner workings of that. Elapsed time is the difference between the current time and the start time, and the best practice here is to use this time function that's called ticks_diff rather than just taking one from another. And you also have to be aware as well that if you have a microcontroller running for quite a long time, the time value will actually wrap around, so you'll get this weird thing, a bit like on a car when the if you've done like over 100,000 miles and it can only do like 999 or something, it'll look like you've got like 0 miles on the clock. And it's that kind of same concept there. Okay, so there's loads of different bits and pieces in here that just set various different internal things, but the thing that does all the work is the tick function. And this is surprisingly simple now. So this says if the elapsed time in seconds is greater than the duration, so again, if we've gone past our duration, we just need to quickly set the current angle to be the target angle. Otherwise, we need to work out what the current angle should be. So set the angle to be the easing function's returned value, and we pass in the elapsed time in seconds to that. And if the current angle equals the target angle, we can return true, and if it's not, we can return false. And that's it. So very simple to do this. So we can go back and we can play around with the duration on our frying pan thing. So if we go back up here, so instead of it being 0.25, I used to just change values like this, but I saw a really nice technique that somebody taught me. Who's a proper programmer, they always comment out the value they want to change so that they know what it was, just in case they forget. So if we now set this to be 3 seconds and we run our code again, so if we get our little, in fact, let's go from the side view. I'm going to click on the run button now. So it's going to then, over a period of time, move it, and you can see that the easing is being applied there because it starts off slowly, moves it and gets faster. We can slow that down even further. Let's do it over like 5 seconds, and if I move him sort of side on, you might be able to see that a little bit easier. So it gets faster as the time goes on, and we can apply a different let's do the linear tween. So what I'll do on the code on here, I've got all these different commented out transitions. So I can basically just uncomment that one and then comment out the one down here, or the quint one, and I'll put on there this one works, just so that I remember. And if we run this code now, it's going to be the same. Oops, let me go to that camera there and run that again. You'll see there's no easing being applied, and he's basically just moving at the same speed. It doesn't slow down or speed up, it's just the same. And let's try an ease in, ease out quint. So if I go over here again, I can comment out that one, comment out that one. So we're now going to do an ease in, out quint. Let's go back to here and let's run this. So you can see there the easing is being applied. It's a lot easier to see in sort of slow time. So it's going slow, speeding up, and then going slow. So what I discovered, to flip pancakes, what we need is an ease in. So we want it to, if I can demonstrate with something that's not a pan, use this box here. So if we want to flip it, we want to sort of start off slow and then very quickly ramp up and then stop, so that the pancake will get to that position and the momentum will carry it on. And the edge of the pancake is ever so slightly in the rim of the pan, that momentum will keep it up and it will flip over into the back of the pan. So that's that's the sort of physics we're trying to aim for there. So if I now go back and I change our code to be, in fact, let's just do that on here. Where are we? There we go. If I just comment that back out. And so we're back at 0.25. That seemed to be the correct one when I was experimenting. And let's go back to this view here. If we can get that camera a bit closer so we can see what's going on a bit easier. It's very small. It is a messy desk, I don't care. Right, so let's move our, let's run our code. Now, I think as I've moved him, that's also come off ever so slightly. So we just need that pan to be ever so slightly flat. It'll probably work better as well if he's raised up off the ground ever so slightly. So if I just put this on this battery like that, so that his frying pan can move a bit more free, that should also help a little bit. There we go. So you can see there, he can flip his pancake. It's a bit easier to see the X. So the X is face down. If I flip that again, let's see if we can get him to flip it. It depends on where it starts, I guess. Let's put it over there. Oh, he's flipped it out. It's not a very good, chef. Right, let's just try again. Oh, let's try it at the back of the pan. Let's try it that way there. Yep, he did it. So the back of the pan seems to work okay. If I put that there, he seems to be flipping that okay. There we go. This is so much fun. And we can move his other arm as well. He's got two arms. If we go back to our captain's table over here, there's a second servo which I've set up as S2. If I move this down here, S2 is his other arm. This is his sort of spatula arm. So if we come down here and we this is where it gets fun. We can have two things happening at the same time, and the code will be cool with this. So let me just go up here. Let's do them in different directions. If I say, let's say S2 dot duration in seconds equals 0.25. Let's do the same speed. Actually, let's do that 3 seconds. And let's set S2. And let's just basically just copy this code here, but change it to S2. And then let's set the S2 dot transition. Let's have ease in sign, or ease in out sign, like that. And let's also do S2 dot tick start, and then in our loop down here, so let's change our code. So while not pan arm tick or S2 dot tick and S2 dot tick, let's do S2 dot tick like this. Okay, let's run this and see what happens. And let's get on to this view here so we can see both of his arms. Oh, he just dropped the pan down. Right, so what have I done wrong there? Let's. What was that? Somebody saying?
No, I'm just saying
Oh.
it's too much for him to compute. Dropped in shock.
What have I done wrong? Have I not set the start and end position? Let me see. So we set the duration. We don't need to calibrate it, that's fine. I'm just looking through the code on here just to see if there's anything I've missed off. So we've got the transition, we've got the start, and then we tick. Let's just try all on there to see if that makes any difference. I'm just looking across, that doesn't work either, so I'll tell you what, let's just get rid of the pan arm tick and let's do S2 tick. Let's get over to here. So you can see his little arm move then. Let's run that again. So he's flipping and then his arm's moving down. So what we need to do is make a start position on that second one. So what we can do is we can cheat on here. We can say S2 dot angle equals, and let's start out with, let's the opposite of that. So let's go for 50, for example, and see if that works. Let's try.
If you snap that thing, I'll laugh.
It will snap if there's too much pressure applied to it, for sure. Let's move him a little bit that way so you can see his little frying pan thing. But yeah, you get the idea. We can basically just play around with this so that we can make one arm do one thing and one arm do the other thing at the same time, because it can all happen within the same loop because they're independent, and the loop will carry on as much as we need it to. Cool. So what else do I want to show you on this? Let's go back to our notes and see what else we have. So that's the Pancake bot. So if you've not joined us on Discord, you're missing out. We've got a really vibrant community of people on there helping each other out with various different coding problems, sharing robots that they built and so on. Really, really great place to sort of hang out. I always wish I could spend all the time I have on there. So if you're not a member of that already, head over to kesrobots.com/discord. You'll get a little sign up link. It'll send it to your email and you can join the Discord group there. And if you're not following me on social media, you can do that in various different ways. I'm on TikTok. I do a little fun videos. I think the pancake flipping one is on there, and any other basically that I do. I do a little snapshot, a little video for TikTok. So I'm Kevin McAleer 6 on TikTok. On Instagram, I'm at Kevin McAleer. On Twitter, I'm at Kev's Mac, and I probably do most of my tweeting and social media stuff on Twitter. And I'm also on Mastodon on at Kev's Mac at Mastodon Social, so you can follow me on there too. And if you do follow me, again, that just helps share out the content I create. It helps grow the channel. And if you want to help support the channel financially, you can do that in a number of different ways. If you're watching this on a replay, you can do a super thanks. There's a little super thanks button that'll show up just at the bottom of the screen. Depends what platform you're on, I guess. If you're watching live, you can do a super chat. I'm going to switch back on the stream elements thing so we can see those as they come in. And you can also buy me a coffee. If you want to buy me a physical real coffee, you can go to kezrobots.com/coffee, and you'll see all the details on how to do that there. You can also join the YouTube membership program. There's a growing number of people that are joining the YouTube membership program, and again, that just helps me be able to buy all these various different bits and pieces that I need to get from various places. These things are not cheap, so every little helps with that. Okay, let's get to our next one. So yes, the supporters. So these are the people who've already supported the channel. Just want to give them a shout out. So we have, let's start on the left-hand side. We've got Braun SL, we've got Carol, we have Hans from Cheerlights, we've got Justine Lutz, we've got Roland, and then members, we've got a bit of doubling up there. We've got John Rank, we have Tom, we have Keith, we've got Shemi, we have Steve. Hey Steve. We have YouTube members. We've got a growing number of people on there. So we've got Jose, we have Dale from Hybrid Robotics, we've got Skipper Banks, we've got Sadiq, we've got Jeff, W. Peabody, Bill, Hans from Cheerlights, we have Michael, we have Fraser, Johan, we have John Paul, and we have Tom as well. So thank you so much. If you want to get your name in the credits here, just head over to kezrobots.com/credits and you can do that there. Okay, and I think that's everything I've got for you on the main show. Yep, Finn, that means we've done on all the things. This was so much fun to do, and really it was just to try and get, trying to stop my Boobal's eyes from burning out, which Boobal's just here on the, you can just see there, if I plug him into a battery, in fact that battery that robot sat on, I've got these really great little on-off switches. So I was just showing at the very beginning of the stream. So these little on-off switches can sit in between like a USB cable. So there's like a female and male connector, and you basically got a nice switch on there. So you can see that these open quite wide. If I reduce the power when they come on, let's just turn it on, and then when I turn off the power, I can see those eyelids ever so slightly ease back, and that means that they're under too much sort of load and pressure when they open back all the way like that. And I need to fix that. So really that was the genesis of why I wanted to look at Servo Easing, and I thought let's do a show about that because it's quite a useful and fun thing to do. So this is the point in the video. If you're watching this on replay, I'll say thank you so much for watching, and I shall see you next time. And if you're watching live, let's have a look and see what people have been talking about. Hopefully the bandwidth issue has resolved itself. It looks great from the stream statistics I can see on the screen there. Cool. So let's see what people have been talking about. So let's see. So hey there. Hey Colin. Colin, you got this. Watching from the US. Got Sparky in the house in the UK. So whereabouts in the UK are you, Sparky? I'm up north. You can probably tell by the accent. I've got Roland. How are you doing? And Adam, who needs a holiday. We've got Alexander as well. And let's see. We've got Steve as well. Hey Steve, how's it going? And of course we've got Laurie. Hey Laurie, let's flip some pancakes. We're going to have some pancakes after the show, so we're not going to hang around too long because there's pancakes waiting for us. Hey Richard, how's it going? And we've got Daniel as well from Brazil. Hey Daniel. So yeah, Richard was saying there's a Tony robot that flipped coins into its mouth, wasn't there? Maybe we should make a pancake version. It's quite hard to do reliably. I guess if you've got everything so it can fall into a dedicated slot, and when it flips, the area it's flipping into to catch it is wide enough, and things should be reliable and you should be able to do it repeatably. But you know, things I'm playing with here are not very reliable. I don't think they're
Base, so it falls.
exactly. Yeah, you need like a curved base. You need something for it to sort of fall into reliably. And then at the moment, the servo that I've got connected up, I've not even wired that in, so I can manually adjust this without adjusting that servo horn. The friction between that and that is enough for it to work somewhat reliably, reliable enough for the show. So Adam was having a problem with I2C, got an error 116E timeout. No idea. I would have to know what the code is, what the component is, what the thing you plug it into, to be able to answer any of those questions. Yeah. So yes, stupid, unhelpful MicroPython errors. If you reach out to Matt and the MicroPython team, I'm sure they can help you get better error messages, but it might be more to do with the library that you're using if they've not written good stuff on there. I know Python 10, Python 11, that 3.11, 3.10, I know that one of the improvements on that was that the error messages were far better. So Adam says, I've got several projects sat on my bench ready. Awesome. So the great thing is you can take these Servo Easing libraries and just like cram it in and it will just work. So you can just make them work. You don't have to understand all the maths behind it. I don't claim to. Hey there. So Richard says, currently making a sandwich while watching. What kind of sandwich is it? We need to know facts. Pancake Tuesday, Hospital Wednesday. All this talk of pancakes. So yeah, thanks for dropping into the channel. Also, were you in Laurie? Were you in Adam's channel before? And also Adam's got a great channel there. Love mailbag. So I have so much stuff in my mailbag this week. So I had a problem with my 3D printer. I don't know if you can actually see from here. If I just grab this and sort of point it at there, this is a real mess. It's all like stringy and just not very nice. And it seems to be the gear that pulls the filament through. I don't know what you would actually call that, just like the feed gear or something, the extruder gear. That doesn't work very well. So I've ordered these new parts, and these ones have like two mechanisms. So rather than having one that's got the teeth on it and one that's just like smooth, this one's got two, and it requires half the amount of force because both are moving in tandem. So I've got that, and I've also got like a new Capricorn Golden tube as well, because I think the other tube might be a little bit messed up now. I was trying to see if I had any of the pieces of wire. So this is like a piece of the filament straight out of the printer, and you will get like a tiny bit of like, I call it like a zip tie effect. So it looks like this like tiny little teeth marks. If you run your finger against it, you can hear that it's like serrated, but it's like unevenly squished on here. And this is good quality filament, so I know it's not the filament itself. I did have some issues with the Bowden tube. If the Bowden tube isn't like completely flat when you chop it off, and I've got a special tool just for doing that chopping, then you get filaments like easing out between it, and that will cause drag as the filament goes in, and then that drag means that it ends up chewing the filament, and the whole thing just, it's horrible. So hopefully that's going to fix it. That's one of the things I got for my mailbag. The other one was I got a whole bunch of parts from Pimroni. They're sponsoring the next Bubo 2T2, which is the new version of Bubo, which I've got just behind me there. It's not printed out yet. So they've sent all the parts needed to build the second one, including a new Raspberry Pi 4, 2 gig. It also has the Servo 2040, which we've been playing with today, and a whole bunch of the Adafruit NeoPixel eyes. There's also the camera module 3 wide, and the camera cable that goes with that. I think that's everything. I basically got two of those extruders because I've got two 3D printers, so I bought two lots of them. And what else I bought? I also bought some what are these? These are like little power boards for... Somebody reached out to me about the SMARS robot, and they wanted to be able to build like a SMARS robot but without using the Arduino and using MicroPython and Picos. So I've got these, let's just open this up and show you what it is. These tiny little boards. I've used these in the past. I think they're like L928 boards, something like that. I think it says on that side. No, it's very, very simple, and they're also very, very, very cheap. And they're pretty reliable. So you can plug the motors into that side, motor A, motor B, and then on this side you've got these int1, int2, int3 and int4, and they're for just controlling each of the motors. So you can put 5 volts into that from like your battery power supply, and then you can send it signals to turn the motors on and off, and you can make robots really small with these as well. So that's instead of like the Servo 2040. These things are like if you buy them from AliExpress, they're like pennies, like 20p or something like that. Obviously, it takes a while to come. They're obviously not on the same kind of quality or complexity as a Servo 2040. They're not really comparing like with like there, but I've got a whole bunch of them to play about with as well. Pink hand waving. Is that like an emoji thing? They come through as literally text there. I don't know why that is, but yep. So Adam says you skinned it. I wonder if it feels cool without skinned it.
It was the image you had on it.
Oh, yes, the servo. I had so much fun with Fusion 360 modelling that out. I took... That's my little robot vacuum cleaner there beeping. So yeah, I took an actual servo apart and I thought I would like this in 3D so I can sort of render it out nicely. So that's what I did. So yeah, I know the stream was dropping earlier. Hopefully that's all fixed now and looks good. So what else we got? So Adam says, yes, what are you watching it on? All right, Safari, browser talk. Just refresh the stream. That's what Syndicate used to say back in the day, wasn't it? Yeah, just refresh the stream. But I think there was something going on our end, but it's sorted itself out now. What else have we got on here? So yeah, buffering, never seen it under Windows. So Adam was saying, I run my profile test on a SG90 at 50 megahertz and mine were 3075 and 135 milliseconds. Ah, interesting. Yeah, and I found I used the PCA 9685 board. There it is. Quite a lot for doing servo stuff. So these are very, very cheap. These are like pulse width modulation. You can put like an external power supply in the top there, and you've got 16 different servo connectors there, and then you basically just got like these cables that come out, and you can just use like I2C to control it. And you can actually daisy chain these together, so you can have as many as you like. You can have quite a number of these added together, and these will go between like 3 volts, 5 volts, up to, what does it say there, 6 volts maximum. That's for the input. Yeah, these are great. These are, I've used these in quite a few projects, but I don't tend to use them as much now. Now we've got things like the Servo 2040 with a processor on board. You've just got one board and it works very reliably, so I use that in that way. So yeah, hey Dale, how's it going? Let's see what else we've got on here. So you find the audio occasionally pops, very faint, no point checking it now. I wonder what that could be then. That might be just me hitting the microphone. It could be an issue with the audio, I'm not sure. It could be, there is echo cancellation on here because I've got my Mac right in front of the microphone, and there's like an option on the streaming software I use to make sure you don't get any echo feedback from the speaker through the microphone. Might be to do with that perhaps, I'm not sure. So hey Wayne, how's it going? Let's see what else we got on here. Thanks for letting me know about the video quality before, that's good. Richard's about 4 or 5 seconds behind, interesting. So I have the latency on ultra low, so it should be like about a second or less ideally. So yeah, delayed by 3 seconds, so that's probably YouTube just trying to buffer everything up and keep it all going, so that's just delayed. So very easy to burn out 9-gram motors, absolutely. So those 9-gram motors, that they're not designed for a lot of weight. These ones, I find these DS929s are pretty strong. They're still only I guess like 9, let's see what it says on there, or 2 kilograms. So this can do quite a lot more torque. These are my preferred ones to use rather than any other type. The ones that are in the Chef bot over there, Pancake bot, they're like another type again that I got from I think the Pi Hut. But yeah, some ports have a TIX max value. Interesting. So yeah, you definitely need to get some Servo 2040 boards. They are the best board for plugging any kind of servos into for sure. Adam says wraparound in computing in the Millennium Bug. Kind of is really, isn't it? And there's a Unix one coming up in is it 2030 something or other? If I had a servo that was at 90 degrees and I wanted it to go to 180, how would I move this? So you basically just set the start value as 90 and the end value is 180, and then just make it tick, and it will do that for whatever duration you put that into. So it depends on many things. So hopefully I've shown you that in the code before. So I'm going to have a play with this. I have several servos. It's really good fun. It's one of the things that's why I built it into a class, that SuperServer, so I can then just like forget about how I did it and it will just work. So did I drop anything in the stream today? I don't recall dropping anything. Do the pancakes count? I don't know. I had to pick them up. It flipped them. Don't forget to click the thumbs up. Thank you for that. So we've got Astra there as well. Hey, how's it going? So there should be an error messages table for MicroPython. I think there might be. Have you checked the documentation? I know that they have an extensive list of all the error messages that they have that are in there. Let me know if you can't find that. No library existed, so using raw I2C read and I2C write at the lowest level. Wow, that's interesting. Yeah, that you can get all kinds of errors doing that if the I2C bus isn't ready, or yeah, that's pretty low level stuff, that, isn't it? So it's a non-existent sandwich. Was it that good? The extruder gear, thank you, Adam. Yes, that's what that thing is called. Bond textile. So have you tried to clear the extruder gear? They get clogged up. So yes, I got a wire brush and brushed the. It's like a little brass type thing. I think that maybe has come up a bit soft over time. This is my oldest printer now. It has printed a lot of stuff, and I could see it was doing that sort of clicking thing where it sort of jumps back. It's one of the disadvantages of like a Bowden extruder, but yeah. Alex wants to have a swivel octopus. You want to get one? I'll print one of those out. When I fix that, that'll be the first thing that prints on that printer. Right, I promise. Adam's got an M5 Stack sponsored video coming soon. Awesome. I've still got all that stuff you sent me, Adam, from M5. I don't know what to do with it, all the development board stuff. I didn't know if it was like super secret or not, so it's just in my drawer at the moment. So one thing about I getting my mail is junk mail, obviously doing something wrong. So what you need to do, Richard, is just spend thousands of hours, like hundreds of thousands of hours, just cranking out content, and then people will start sending you stuff. That was my model. I think my favourite thing so far is that little robot dog that I got sent there. That was quite a cool thing to get sent. That and probably the Picade. I mean, man alive, that's a pretty awesome piece of equipment. So I always like getting the secret packages that I'm not allowed to talk about from various companies. And when I can talk about them, it's just the best thing. So I may or may not have some of those. From many companies, in fact. 3D printed skeleton necklace for Halloween. Sign the petition, print the octopus. It's happening. You didn't even need to do that. I'd already said yes. Anything for Alex, no problem. So Richard says he'll print it out, but he needs to get another bigger 3D printer.
A shark too.
A shark?
As well.
A shark, okay. Yay for the octopus. Yes, too. I saw the pink, the print with suckers pink, and then change the filament halfway through. Oh, right, yeah.
So the 2 layers of pink.
Yeah. It's not easy changing filament halfway through. I'll let you know that. It's really.
Robots.
It's still not easy to do, honestly. I probably need to get a special printer with like 2 filament things that feed in. Yes. So I've got one of those adapter boards on the shelf behind me that has an Arduino version in a custom PCB. The adapter boards. Which adapter board is that? Oh, the PCA 9685 board that I've now put down and cannot find anymore. Yes, that thing. PCA 9685 board. These are really cool. I think the quad robot that's up there, that's got a couple of those in it. Huday, how's it going? So Rich says I'm on a 10 seconds behind as the stream frozen. Probably YouTube or ISP. It's probably my ISP or something to do with my router, perhaps, maybe. Adam says that, they say in the Field of Dreams, if you build it, they will come. This is true. This is so true. And everybody should be on MicroPython Discord too. There's work being done to simplify porting CircuitPython libraries. So that's really cool. So I'm really glad that there's a lot of work being done to sort of join those 2 libraries together, because there is so much good stuff from both sides there. And also companies like Pimroni as well, who bring quite a lot to the table too. So Adam says 5-second rule, the 5-second tool rule, 5 seconds and then it vanishes. That's it. It's very true. I've now I opened up a little parcel and now I can't find where this goes. So I'm going to have to put that back in there. Otherwise I'll lose that. Also, I find like boxes full of stuff and then I think, oh wow, there's like some really cool stuff in here. I've not played with that like ever.
Isn't all of these
it's basically all those boxes that are down there that we're not allowed to talk about because they're all secret.
I thought you meant
Those
these
ones. Oh no, them ones. They're the boxes of shame. That's where things that. Well, some of them have got tools, and they're all like the heavy tools in those ones. I think that's like the hammers and drills and stuff like that. That's probably one of shame. Yeah, that one there.
What is that?
I think we should rebuild that one.
What is it?
That. I'm gonna hand it here.
Oh my
Go on, drag it. There you go.
god. Oh my god.
Alex dropped something. Right. So this was a robot that I was building that I never finished because I ran out of ideas on how to fix it. So I can probably return back to this and get it working. So this was like a crab robot. And you got his eyes there. Awesome. So his eyes would be in there. He's actually got like a little plate and like another bit that goes over the top, so he looks like a proper crab. And he has these little grabby arm things. Like he's got little crab fingers as well. And he would sort of do that kind of thing. And he would kind of crawl along with just 2 sets of arms. And then inside would be the Raspberry Pi Pico. And at the time when I designed this, I didn't have the design ability to engineer everything that I needed to make this like a totally enclosed robot. Look, that has a 9685 board for all the servos as well. So we could probably return back to that crab robot, Pico Crab, and make it work. Do a Pico Crab version 2. That'd probably be quite a fun robot to get working as well. And I can probably show you the differences between the previous version and the new version. So I like to keep all my old things because sometimes I return back to them. So it looks like a mod for a smart bot. Yes, a SMARS quad even, and you're absolutely right. So those arms are essentially, that is essentially the SMARS quad arm, because it worked as a design, and I had the design files to make that work. These use those sort of cheap SG90s, but they do work fine, and you can see there they're all plugged into that mess of wires there as well. So we can probably get that working. So we need an episode on the Box of Shame. I have previously done one on the Box of Shame. There's probably more in it now, but I've got more stick-with-itness now, and I've got a bit better skill, so I can probably fix more of the issues that I come up against. So like Bubo Tutti, for example, there's been like 3 iterations of that so far, 3 different bits, but that was more down to the printer failing. So these are the sort of eyes and the eye things that stopped printing for various reasons. Electricians coming to do things. So yes, Alex says I've got 8 boxes of shame. It should be a whole season. Yes, box of shame. Laurie's for that too. So Dale's just found Laurie's YouTube channel. Yeah, Laurie's got a really cool channel. I noticed you did the unboxing on one of the videos I watched, Laurie. Awesome. So Julian says thanks for sharing. No problem. And Laurie's thanking Dale there for visiting as well. Great, thank you so much for watching. I really enjoyed today's show. It was really fun to show you the pancake flipping robot. And I love the fact we got him to sort of reliably flip it quite a few times on the stream. I thought we were going to go through and he just wouldn't do it at all. But I've captured it and put it onto TikTok and Twitter and Mastodon and Instagram, a little video clip, and I think also YouTube Shorts as well, of it actually doing it. So you can see there it's not just a fluke. So yes, thanks everybody. I shall see you next time. So thanks for watching. Bye for now.